Sandy, thank you very much for this nice introduction. Ladies and gentlemen, it is my pleasure and honor to be here today again. This is my fifth visit to your wonderful country. And every time I come here, I visit Foundries, and really, I learn a lot. You have a long history of foundry tradition and science. Really, I am here to learn as well as to give some of what we are having now in our institute. I want to talk about how RTOs, research and technology organizations, can interact with the foundry industry in our country. I decided to give some examples, case studies from our institute. How have we been interacting with our foundry industry over 35 years? And it is not secret, after Sandy revealed my own age, I have been working now 50 years in metallurgy of cast iron. And now I am going to go through some of our activities. First of all, I introduce our institute. No, it is not working. Oh, yes, that is our institute, and you can agree with me that it is beautiful place. We are in the desert. We received this piece of desert 35 years ago, and we were asked to build up our institute here. And that's how we could manage to transform the piece of desert in a really a very nice place, which we are very proud of. About my talk today, I'm going to give an idea about how could we manage to keep a certain balance between academic work in the foundry industry and some industrial applications, technology transfer, development of new casting alloys. How could we make use of our international collaboration projects to serve our foundry industry? How could we develop some standard training courses in different areas of cast iron to serve our country and other countries? And from there, we can really talk together about where to start our collaboration. I start with introducing our institute. We are a Central Metallurgical Research and Development Institute affiliated to our Ministry of Scientific Research. We have been established in late 70s of the last century. We have 4 main departments: mineral technology, metal technology, advanced materials, manufacturing technology, which involves 4 different groups: casting technology, where I came from, welding technology and non-destructive testing, powder technology, and rapid prototyping and 3D manufacturing. That is the main skeleton of our activities. I got my PhD from Moscow in 1972. Since I came back home, I started to establish the first foundry research facilities in the area, and we have done some activities, but the real start was with the establishment of our experimental foundry, with a capacity of about from 600 to 700 tons a year of castings. Why did we decide to have our own foundry? I can just recall that 35 years ago, we made a study for the spare part situation in our country. And we found that we have a real problem with the spare part. First of all, we are not an industrial country. We need limited numbers of very wide variety of castings as spare parts, as any developing countries. Most of our foundry, of our machinery are old. It is very difficult to get spares from the original supplier. Even if we have original suppliers, usually they have some monopoly of original suppliers, and they dictate the prices they want. And most cases, it is exaggerated prices. We have some attempts of local manufacturing with spare parts. Some were made by success, and most of them were failures. You know that lack of spare parts may lead to a frequent stoppage of production lines and lower productivity. very often we have noticed that you have sometimes to scrap a very expensive machinery because of lack of one cheap spare part. That's why we decided to have our own own experimental foundry in our institute. And this was established with a very kind assistance of the Dutch government who sponsored this experimental foundry. And we have really modern equipment, but that time it was a modern foundry. Now we are now thinking about updating most of it. It is now working for 35 years. No, I think yes, we have induction furnaces, serial induction furnace from 100 kilos up to half ton. We have jolting machines. We have this automatic cold box machine for core making. We have sand preparation plant, 8 tons per hour. We have a high pressure die casting machine, and this is one of typical products, which is motor covers for aluminum and magnesium alloys. We have a CNC cutting machine. This foundry now is working. Sometimes it is producing parts for the industry when these parts are needed in numbers within our capacity. Otherwise, we have to develop technology in our foundry and transfer it to commercial foundries. The real reason behind thinking about the experimental foundry that we have over 40 years experience in development and selection of casting alloys. That's why we can always select the most suitable alloy for any casting. We have production flexibility and possibility of limited production. If somebody needs one piece of casting, we do it, because this one piece of casting may be enough to put a complete production line in operation after stopping for a long time. We have excellent facilities of control, analysis, and characterization of alloys. We have different spectrometers for spontaneous chemical analysis. We have different metallurgy, scanning microscope, transmission electron microscope, image analysis, and so on. Very modern equipment, actually. We have different X-ray units for characterization. Even we have thin film X-ray diffraction. We have other equipment, inductive ICP, we have carbon sulfur analysis, we have gas analysis, oxygen, nitrogen, alloys, differential thermal analysis, and so on. We have a new lab for quenching diatometer to study the phase transformation in casting alloy, which is a very advanced. You can heat and quench from any temperature to fix the structure during heating or during solidification. We have a complete mechanical testing lab with computerized impact testing, with a universal testing machine, tribometer. We have a new tribological measurement center to measure different types of wear resistance of alloys. We have a Gleipel test to stimulate almost all metallurgical processes, forging, extrusion, welding, casting, and so on. We have the Kessler dynamometer to measure the cutting force during machining of casting alloys. To summarize the main objectives of our experimental foundry, first of all, to carry out research and development programs. That's our main function. To produce prototype castings for the experimental foundries, for the commercial foundries before they start commercial production. Develop of new casting alloys. Technology transfer of new casting to the foundry industry. Training, both local and regional. Production of spare parts for the different industrial sectors. This is we started with the last one, production in our back mind. The requirement was so limited. Now this is the main activity of our foundry, mainly because of the difficulty with hard currency in our country now. Most of some of casting requirements are made now in our foundry, instead of being imported from abroad. Now I give some examples very quickly about some of the spare parts produced in our foundry. The first one, this one. We are the only producers of these track shoes of the tanks for our military forces. This is from high manganese steel. This is already going on for 25 years. The same product can be used for the agricultural equipment, for tractors. We are producing copper bearings, digging teeth for our Suez Canal development, heat exchangers, glass molds for a special type of cast iron, different spare parts for the airlock for the grain milling machines, which now is being used instead of the imported one, and different spare parts for our chemical industry sector, spare parts for the railway sector, for the metallurgical sector. And I now go to the technology transfer of new casting products. I give some examples. We started actually in 1983 with introduction of ductile cast iron first time to our foundries. You know, ductile cast iron is just, if you look at the photo at the right hand side, it's gray cast iron, where the carbon or the graphite exists in the form of flakes with sharp edge or sharp tips, which acts as stress concentrators. That's why gray cast iron is known as a weak and brittle material. In 1949, with the first development of ductile iron or spheroidal graphite iron with very small additions of magnesium up to 0.04, 0.05%, the graphite flakes were transformed to spheroidal graphite. That's why and then to neutralize the detrimental effect of the graphite flakes. And we developed this technology because addition of magnesium is not very easy. It is a very pyro process and gives sometimes some explosions and some dangerous effects. We developed this very safe technology, which we call the vortex process, where we pour, where we pour the molten metal in this tundish, and the metal will go to this compartment tangentially. It will rotate in a vortex, and then we add the magnesium alloy through this hopper in the middle of the vortex. And then the reaction would be very mild. As you see, people are standing beside it with no danger at all. We have introduced this technology into 8 Egyptian foundries, and in 2009, we were producing 100,000 tons per year of ductile iron using this technology, and this represented about 35% of the casting production in Egypt. Pipes, royals, fittings, automotive parts, and so on. Then we moved to the textile spare parts. At the time, we had one of our textile integrated companies employing about 35,000 laborers. It was one of the largest in the world, and they have some problems with spare parts. Spare parts, as you see, of the textile machinery are rather thin, 2-3 millimeters. It is not very easy to cast. And the decision were taken to replace the malleable iron castings into ductile iron castings in 1986. And our institute were in charge of technology transfer, manufacturing of the vortex unit in our institute, 6 months supervision of production, and then training. And since 1987-86, this company totally stopped the imports of casting spare parts. Now they are even producing spare parts for other textile sister companies. Now we move to one of the biggest challenges, ductile iron rolls. Without having local technology for ductile iron roll manufacturing, any country is in danger, really. And this happened in some African countries, like I remember Nigeria and Algeria, where steel industry stopped completely because of the lack of local technology and lack of hard currency required to import these very economically and strategically important castings. In Egypt now we are reaching 10 to 12 million tons per year, and they need about 7,000 tons of rolls per year. It is a very important product strategically and economically. Thousands of rolls were produced. We have produced about 5,000 rolls until now in different foundries, both in single and double rolled, as I am going to explain now. And several research projects were planned in our institute to conduct research projects aiming at increasing the competitiveness of these products in both Egyptian market as well as international market. We were aiming at improving the performance or lowering the production cost and thus increasing the competitiveness. Sorry, I was supposed to have some animation here to explain. You know the rolling mill. the steel billet is going through the first group of rolls, which we call the roughing groups, then the intermediate stands, roughing group of stands, and finally the finishing stand. In the first roughing group, the reduction ratio is very high. That means the mechanical loading in the rolls are very high, enormous loading. And that's why the roll material here should withstand fracture toughness. They should be able to resist fracture, mechanical fracture. The abrasion here is not important, because if the distance between the two rolls will increase due to the wear of the roll material, this will be adjusted in the following stands. But in the finishing stands, which determine the final dimensions of the rolled product, the abrasion resistance is very important, and the mechanical loading here is minor. You know, then in the roughing stands and finishing stand, you need material of contradictory properties, because fracture toughness and wear resistance don't come together. They are contradictory properties. I mean, not only that, if you look at in the same roll, you'd have the roll. Sorry, I give you some picture of the roll. Yes, first. In this roll, the roll is consisting of the main body of the barrel, what you call the barrel, which achieved the rolling process, and the two necks, through which the roll is being rotated. The roll body or the barrel is subjected to abrasion the whole day. Steel is going forth and back the whole day, and they should be resisting to high temperature and abrasion at high temperature. The necks through which the roll is rotated, they should withstand mechanical loading, fracture toughness. You mean even in the same roll, you have contradictory problems between the roll barrel and the roll necks, and that's which makes production of the tire rolls a very special high-tech process. We started this in 1987, and the challenge was the metallurgical demands are very complicated. The rolls are subjected to abrasion. They are subjected to thermal effects during the cooling and heating of the steel by the steel product, also to mechanical stresses, which may lead to the breakage of the roll during service. And these catastrophic accidents may happen if you don't follow the technical scientific rules to cast the rolls. Then the metallurgical demands you may summarize in high wear resistance and long life, high resistance to fracture at the necks, insensitivity to fire cracking due to thermal fatigue, insensitivity to spalling, in good surface quality, and adequate bite between the rolled material and the rolled stuff. The attainment of a high quality rolled product is cumulative throughout the whole rolling operation and depends on the correct type and the quality of roll being located in each successive stand of the rolling train. And the metallurgical, mechanical, and physical demands placed on rolling mill rolls are quite complex, particularly in modern rolling mills. With the current knowledge, it is not difficult to achieve any level of abrasion resistance, not difficult to achieve any level of fracture toughness. The real challenge here is the combination of both contradictory properties. That's why actually now they call the roll metallurgy as the metallurgy of compromises. First of all, to design a material of the roll, you have to know the function or role of every microstructural constituents of the roll material to achieve any of the metallurgical demands of the roll. We have in microstructure ferrite, you have laminar perlite, spheroidal perlite, you have bainite, martensite, carbide, and graphite. And we have to know the role of each microstructural constituents on the different metallurgical demands of the roll. The breakage, the resistance to fracture, toughness, the bite, good grip, and the wear and the abrasion resistance. We have to know the function of each of these constituents on each of those properties. Then just me very quickly I give you how we cast. This also should have been in animation, but I can give you. We cast the roll vertical like that. You need the surface barrel with a high abrasion resistance. That means high hardness, and the next you need high fracture toughness with lower hardness, and that's why we cast the main body or the roll. The roll barrel in cast iron chill. This is the black one. Big cast iron mold die, or we call it the chill, because the main function is to increase the cooling rate of the iron and to promote the formation of carbides at the surface of the barrel. Meanwhile, the two necks, the lower and the upper one, are cast in green sand molds. Lower solidification rate will give you lower amounts of carbines and higher fracture toughness. We pour the metal from the top, and the metal will come and fill the. This is possible, but if you need high hardness at the roll surface, you have to add some to increase the carbon content to form carbides, to add some chromium and some nickel, chromium to form chromium carbides with the carbon, and nickel to enhance the formation of martensite on the surface for higher hardness. If you do that, if you increase carbon, chromium, and nickel, you will be fine with the barrel, but you will increase the hardness of the necks. And then there's a danger that the necks will be broken during operation, which may lead to catastrophic accidents, really. Then we start to work with not single pour that we pour only one metal in the mold. In the double poured, we have another different technology. We just have the same setup, but we overflow before the top, in the middle of the top neck. And then we cast first very hard material, high in chromium, nickel, and manganese. Fill the mold, leave it for 3.5, 4 minutes, enough to have a solidified, the red layer, solidified shell. Whether the rest of the smooth metal is still liquid. After this, we pour another tough material in the same system here. This should have been shown by animation, but I'm sorry for that. The next soft metal or tough metal will just replace the first metal and take it away and fill the mold cavity. Finally, we have a roll with outer shell very hard, very resistant to abrasion, and a core and necks of tough metal which is resistant to fracture. This is what we call the double poured rolls, and we developed our own technology for that in '89. Sorry, of course it is not so easy process, because the two metals should reach the pouring station at certain time, at certain temperature, because you know, of course, that the cast iron roll solidification, it undergoes first some shrinkage with the formation of austenite, then the formation of graphite, some expansion, and then again contraction after that. And the two metals should expand together and shrink together. Otherwise, if the outer layer is shrinking and the inside is expanding, you will have cracks in the outer layer, and so on. It is very important to have the two metals at the pouring cup at certain time, at certain temperature. This, of course, usually made in foundries with two melting furnaces. One melting furnace melting the high alloyed iron, forming the outer shell, high chromium, up to 1.5 chromium, up to 5% nickel, and the internal metal may be just ductile iron, or maybe even steel. And then usually you have two induction furnaces, one for each metal. Our challenge was that we have only one furnace, and we are supposed to melt the two metals from one furnace. Could have been done if we have first to pour the low alloyed soft metal, then increase the alloying element and pour the second metal. You could have added the alloying element in the furnace, but we couldn't do that. We are pouring first the high alloyed iron and then the low alloyed iron. This was a real challenge that we solved it. Sorry, we have first another challenge, that if we have high alloyed iron at outer shell, to increase the hardness and the abrasion resistance, usually you have white structure without any graphite, mainly carbides and some sort of martensite, as you can see from the structure. The whites are the carbides, and the acicular phase is the martensite, which gives the maximum hardness up to 85 shore hardness. Without graphite in the structure, you have high tendency of fire crack formation. You have very difficult machinability of the rods. We have to develop our technology how to force graphite to precipitate in alloys containing up to 1.5% chromium. Chromium is a very strong carbide stabilizer, and all the carbon in the iron will form carbides. There will not be enough carbon to form graphite interaction, and we had to develop a certain inoculant to force the graphite to form in the spheroidal form, as you see in the outer layer. Thus, we increased the resistance to fracture, we increased the thermal conductivity, and we decreased the tendency for fire crack formation, and we improved the machinability due to the presence of the graphite spheroids. This is how we just explain very quickly. This is the induction furnace in the middle, melting furnace, and we have two ladles. First, we melt the low alloyed iron with, as you see here, chromium 0.3%, for example, nickel is 1.4, and so on. This is the low alloyed iron, which is supposed to form the core of the rod. And we kept away for a while out. And then we added the rest of the alloying element in the furnace, with the chromium up to 1.3, nickel up to about 4%. These are high alloy, supposed to represent the outer shell of the rod. Then we took this, the hard metal, and it was cooled up to 307, and then we poured in the mold to left it for 3-4 minutes to form the outer shell, so the fired shell. At the same time, we took the low alloyed iron, treated it with the vortex process to form spheroidal graphite, ductile iron, and poured it to form the second or the core of the rod. It should have been explained by animation, but unfortunately it doesn't work here. This is, of course, if you have any questions, if you have any interest in this technology, we can discuss it after the lecture. Now the alloy, the hard nickel alloy, we call it hard, is firmly established for casting of outer shell of double pored rolls used in the last stands of hot strip mills, and the precipitation of spheroidal graphite permits the development of hard be used in the early stands where toughness is of higher concern, and the benefits of spheroidal graphite is increased resistance to fire cracking and improved machinability and improved rolling lubrication and roll pipe. We have so many different types of rolls, about 50 or 60 different rolls, but mainly they can be categorized in two groups: definite shell or clear shell rolls and indefinite shell rolls. This hardness gradient of the clear shell, where you have this is the distance from the surface of the barrel, and this is the hardness. You have a layer of clear hardness, clear increase in hardness of clear shell, and then you have a sudden drop in hardness until to the center of the rod. In the other indefinite shell, you have a gradual decrease in hardness between the roll surface and the roll center. Of course, I'm not going to go through this but this different research projects we have conducted to different foundries. We started, of course, with the introduction of ductile iron technology vortex in these foundries. Then we will be able to produce the rolls. Then we try to increase the competitiveness in international markets, either by lowering production cost or by performance improvement. Performance improvement by development of the double pored rolls or the development of hard HG iron. Production cost was decreased by use of sponge iron, the DRI, as replacement of the sorrel, very expensive material. There was a shortage in our country at that time, and we had to find other alternatives. And then improved, we studied machinability of than hard outer shell, because it's a very hard material to machine. Finally, we have Egyptian rolls used in all Egyptian steel mills, and 2 of our foundries started to export rolls to Arab and European steel mills. These are the details of technology of roll and different types of roll with different structures. I think time will not allow me to go in details. And this is a guideline of roll applications for different products. This is for the shaped profiles, and this is for the flat products. And these are some examples of rolls being cast in our foundries. Until now, we have cast about 5,000 rolls for different steel plants. And this shows the evaluation of the rolls in the steel plant. Of course, you don't use the roll for one time. You use it for several thousand tons of steel being rolled. Then you have some cracks on the surface, thermal cracks. Then you take it out of service. You turn it and take 2-3 millimeters to bring the surface to its original condition and put it again in service. And this how this is the number of turnings, first turning, 2 turnings, and this roll was used for about 8 turnings, I think. And each time you plot, the first turning took place after hovering 40,000 tons of steel, and so on, and then you draw this. And this then you each time you count how many millimeters you had to turn to bring the roll to its original condition. And then you divide how many millimeters per 1,000 of tons. And this is the real measure of evaluation of the roll. And this is a curve of really of comparison between our locally produced rolls for a Japanese steel mill in Alexandria compared with Japanese rolls. And this curve was plotted by the Japanese experts in that plant. And it showed that our rolls were slightly better than the imported rolls. Since we started with this company, the company used to purchase 50% of their needs by direct order from this fund. Sorry, what about time? I usually forget about time when I start to go.
Another 5 minutes.
Another?
5 minutes.
5 minutes, okay. This was another one case study of technology transfer. This is another case study. This we have one of the largest aluminium smelters in the region, at least. And you know, this is the photo of this huge smelter. And in the aluminium electrolysis, you use carbon anodes. And these are fixed by a steel fork. And this is the carbon anode, and this is the steel forks which are hanging the carbon anodes in the electrolytic cell. And this hanging taking place through pouring of cast iron in this collar between the steel fork, the steel stub, and the carbon anode. And it was believed before this, we worked with a Russian technology, which believed if you pour cast iron in this very small gap between 2 very strong chilling materials, I mean the carbon anode and the steel stub, the metal should have maximum castability or maximum fluidity. And fluidity is enhanced by phosphorus addition. And they used to use cast iron with 1.4, 1.5 phosphorus. And this really affects very much the electrical conductivity of this joint. And the loss of electrical power happening in the whole electric cell, 50% of this loss happens at this junction. If you improve the electrical conductivity of this junction between the steel stub and the anode and the cast iron collar holding them together, then you will be saving a lot of power and a lot of money. And we started to investigate other alternatives, cast iron instead of high phosphorus iron. And we found that phosphorus is not the proper alloying element. We found this is a simulation of the work where we have this black one is the graphite, represents the graphite anode, and then you have a hole, this steel rod, and you pour the metal between them. And we found that the most important factor here is not the properties of iron or steel. you know, the cast iron when solidifies, we have graphite precipitation. And graphite will exert some expansion forces during solidification. It's a very light material. It occupies a lot of space, volume when forming. And this formation of graphite will increase the contact pressure between the steel and the carbon atom. And this will improve dramatically the electrical conductivity at the junction and will save a lot of money. Actually, the report we have from this big smelter indicates that replacing this color material, which about 2 kilograms, by another cast iron material was enough to save millions of pounds every year. This is another project, and these are people who are working with me. I would like to thank them because we have spent 1 year working together. And then another 2 minutes, or leave it after? After?
Let's do it for after.
Okay. Thank you. I'm ready for any question. We complete after lunch. Okay. Have a nice meal.